Hello everybody, my name is Brani Rusanov and today I'll be speaking about my project. The title is Investigating Cone Beam Computed Tomography, Dose Calculation Accuracy, a comparative study on competing HU calibration techniques. And I'd like to thank my supervisors Godfrey, Mashid and Professor Martin. So just a brief outline of this talk. First I'll cover the background, then move on to purpose, then I'll discuss some problems with CBCTs, and then I'll discuss some image quality improvements for the Hounsfield units and correction techniques. And then I'll discuss some adaptive radiotherapy clinical results, which are a direct, application of my project. And then talk about conclusion and significance. So, with the background motivation for this project is, it relates to the interfractional patient anatomy movement, which can make initial planning parameters inaccurate. And the purpose of this project is to improve or ascertain the optimal CBCT image quality and HU adjustment techniques for applications in dose verification and adaptive radiotherapy. And what I mean by dose verification is a comparison between the planned dose that is initially calculated at the beginning of the procedure and the actually delivered dose on the day of the radiotherapy treatment. And similarly, what I mean by adaptive radiotherapy is the re-optimization of initial planning parameters to better conform to the anatomy of the day. So in any radiotherapy treatment, there are two main goals that make it a successful radiotherapy treatment. And the first is to minimize dose to healthy tissue. And the second goal, which is arguably more important, is to maximize tumor necrosis. And this also relates to the systematic error and the random error in the treatment. So we can't really do much about the random error, that's inherent in the system, but we can do something about systematic error. That is the error that the medical physicists try to minimize. And so every effort should be made to reduce error stemming from systematic sources. Systematic errors from interfractional anatomy motion are caused by patient weight loss, natural organ displacement and deformation, and tumor progression and regression. Current protocols are inadequate to account for such organ motion, as typically wider margins are used to compensate for anatomy changes, but beam misalignment may still persist, which leads to negative outcomes such as cancerous tissue underdosage, excessive healthy tissue necrosis and risk to radiosensitive organs, latent adverse effects, and increased probability of tumor recurrence. So some examples of organ motion, a study by Young and his colleagues investigated the motion or the movement, interfractional movement of the cervix in cervical cancer patients, and they found that the mean range between fractions was 11.2 and 11.3 millimeters in the AP and CC directions. Similarly, for the same patients, an organ at risk is the uterine fundus, and that moved 14.5 and 24.4 millimeters, again in the AP and CC directions. And another study by Philip and his colleagues looked at the prostate, and the prostate moved 10.33 millimeters mean range. This is for a lot of patients they looked at. And so, such movements in soft tissue can only be compensated by extending large margins to the PTV. This can lead to substantial irradiation of healthy tissue. Therefore, it will be helpful if target volumes could be adjusted pre-treatment. This would lead to more sparing of healthy tissue and greater tumor conformity. This is the motivation for adaptive radiotherapy. The purpose of this project is to improve the CBCT image quality parameters so as to make dose verification and adaptive radiotherapy clinically viable. And just quickly, CBCT is cone beam computed tomography, which is an imaging device that uses X-rays and a cone geometry that is mounted on the LINAC gantry. And the image quality is not as good as standard CTs, as will be discussed in a few slides. So what I mean by dose verification is a calculation of a dose of the day. And this is performed by applying the prescribed plan to the pre-treatment CBCT image. Then dose volume statistics are computed and allow the physicists and physicians to observe the accuracy of dose delivery. And again, what I mean by adaptive radiotherapy is If the delivered dose is deemed problematic, the plan is adapted by re-optimizing the margins and target volumes to better match the anatomy of the day. However, major issues with realizing these radiotherapy tools stem from the poor CBCT image quality and unreliable HU to electron density conversions. So I'm going to talk about, first of all, the fundamental, reconstructions that CBCTs undergo. So there are two main methods. The first is filtered back projection. And in filtered back projection, every data point from the flat panel detector represents an array of summed attenuation coefficients. These data points are smeared out back over the array paths, with the result being an image that is representative of the original object. However, filtered back projection is fundamentally flawed due to a number of approximations into tenuous assumptions used to underpin the mathematics of the reconstruction, which collectively degrade the image quality. And with iterative reconstructions, an initial guess is made of the object, either through a crude guesstimate or a filtered back projection. The algorithm then makes some alterations to the guessed object and conducts a forward projection. These computed forward projections are compared to the measured projections, and an error matrix is generated. The next iteration is made in the hopes of minimizing the error matrix and approximating the real data set, thereby producing the image. Iterative reconstructions are superior because they can remove artifacts during the actual reconstruction process and are not propagated through the reconstruction as in filtered back projection. Now I'll talk a little bit about the artifacts that plague CBCTs. So an artifact is a deviation in grayscale value. Since grayscale values correspond to electron densities in CT images, and CBCT images of course, one must correct for artifacts to ensure that valid dose calculations are performed. CBCTs are especially prone to scatter artifacts because of their inherently large cone-shaped field of view, or cone-shaped beam. Scatter is the single greatest reason for bad image quality in CBCTs, and this is especially evident in soft tissue contrast, which makes contouring and diagnostic analysis more difficult as compared to planar CTs. So traditionally they're not at all used for diagnostic purposes. Currently they are mainly used for IGRT applications, which is just aligning the patient and the table such that the beam hits the target. And here, unfortunately, you can't see these images very well. These images are meant to highlight what scatter correction actually does to a CBCT image, and in fact, so A is meant to be no scatter correction, but yeah, it's kind of messed up from the contrast. But the images are meant to show that scatter correction significantly improves the image quality and the HU reliability of CBCT images, and that's done through an iterative reconstruction, which is more effective than filtered back projection. So just again, some typical artifacts that are present in CBCTs. You have ring artifacts, cupping artifacts, streak artifacts, crescent artifacts, and motion artifacts. And all of these they're present in normal CTs, but exemplified in CBCTs, again due to the larger cone shape and just inherent to the modality. So now that we understand how CBCTs have impaired image quality, we can discuss ways to improve it. And in order to address the correction methods about to be presented, I would judge the methods based on their difficulty of implementation, quantitative and qualitative analysis. So when you look at the image, quantitatively, is it better than, or how much better is it to other improvement techniques, and qualitatively, does it actually look better to the human eye? And thirdly, the viability for adoption in the clinical workflow. So before, with every CBCT image, with every CBCT machine, a calibration needs to be performed in order to establish a relationship between the grayscale value and the electron density. Phantoms with tissue equivalent inserts are scanned, and by simultaneously knowing the actual electron density of a given insert and corresponding CT number for that insert, one can generate a plot of HU versus electron density, various materials. Using this curve, future patient scans can be reassigned electron densities based on the measured CT number. However, Calibration scans using tissue equivalent materials are known to be unrepresentative of actual tissue, and therefore a stoichiometric method was developed in the literature, as will be discussed next. So in the stoichiometric method, a relationship between the electron density of tissue equivalent materials in the phantom is made to the actual real electron density of the corresponding human tissue. And an empirical equation is then used that uses the effective atomic number, mass density, and electron density of both the human tissue and the tissue equivalent phantom to derive what the real human the real human tissue HUs would be. And you don't actually need a human to derive these, you need just the phantom. So all future calibrations should follow the stoichiometric method to ensure those calculations are based on attenuation characteristics as close to real human tissue as possible. Next comes the artifact correction step. So typically, scatter destroys HU uniformity in thick regions such as the thorax or pelvis. And so dose calculations performed on non-corrected CBCTs can deviate by as much as 10% compared to planning CTs due to artifacts and, of course, scatter. And this leads us to the first correction method called density override. So the fundamental premise behind density override techniques is predicated on modifying the CBCT image using information from the planning CT. So soft tissues and contoured structures have their HU values replaced with those from the planning CT. And there are several methods that do this, and they will differ in various ways. The first method is called multi-level thresholding. The second method is called histogram matching. The third method is called water-air-bone override. And the fourth method is called region of interest mapping. Another method for correcting or improving the CBCT image quality, in this case, you're actually using the initial planning CT and using deformable image registration by first rigidly translating the planning CT to match the CBCT based on bony anatomy, and thereafter soft tissue structures on the planning CT are deformed to match those seen on the CBCT. Improving CBCT image quality through various artifact and scatter correction methods outlined in the next section, as well as the density override methods in the previous section, will actually improve deformable image registration efficacy because the algorithm can better detect soft tissue structures. And a major advantage of deformable image registration is the automatic deformation of organ contours performed on the planning CT. So this saves manual CBCT organ delineation time, which is an important contention for any adaptive radiotherapy implementation. Another method is called the lookup table method. So in this method, the relative HU for many patient datasets for specific tissues is acquired, averaged and plotted for CBCT versus planning CT modalities on a single graph. The CBCT HUs are then reassigned based off the resulting graph. And another method is called the scatter correction. And this method aims to model scatter and correct the corresponding artifacts of the result. So there are several methods based on the reconstruction used. So with filtered back projection, filters, as suggested by the name filtered back projection, filters are applied and simply they convolute the dataset with empirical models of scatter. With iterative reconstructions, they can model scatter through empirical or Monte Carlo methods, which are more sophisticated and actually lead to better image quality at the end. The resulting scatter model is subtracted from the image, thereby reducing artifacts and improving image quality with respect to contrast. Scatter correction methods can be coupled with the aforementioned correction techniques to further improve the final image. Whoops. Okay. This is a little map of how I will be conducting this project. So I've finished my proposal and literature review, and the next stage will be to acquire phantom and patient CBCT datasets. And after I have those, I will be simultaneously, or not simultaneously, but I will be trying to explore each of the methods outlined. So I will try and evaluate commercial and open source deformable image registration algorithms and see how they perform. I will be exploring iterative reconstruction toolkits. There's actually quite a few of them online as open source sources. I will develop in-house density override techniques, as they're not, I wouldn't say they're too hard to do. I think just a bit of MATLAB coding, and we'll see how that goes. And then, of course, I will explore open source scatter correction toolkits and hopefully apply these to the rest to improve the overall image quality. So I will apply the respective correction techniques to the CBCT datasets, and then I will perform dose calculations and analyze the results. So with these dose calculations, I will perform them first. You have they're performed in a planning CT, so you have your dose volume histograms and whatnot. And then the same calculations methods are performed on the CBCT image, and the aim is to actually compare how close the dose on the CBCT image is to that on the planning CT, and that will tell you how effective whichever method was used to correct the CBCT is. And once those comparisons are made, I will write my report and hopefully publish. So, I guess to highlight the significance of improving CBCT performance, I will discuss a direct application of CBCTs in adaptive radiotherapy. So far, adaptive radiotherapy trials utilize libraries of offline generated plans. Adaptive plans are created using the first few CBCT images acquired in the first few treatment fractions. The images are delineated and planned offline, and then small, medium, and large plans are generated. During the time of treatment, clinicians choose the plan that best suits the anatomy of the day as observed on the CBCT. And results for clinical trials, for example, Ronborg et al., looked at bladder cancer and the rate of bladder filling over 10 minutes. And 10 minutes is well within the typical time for a radiotherapy treatment. And patients were asked to first empty their bladder, and then they analysed how much the bladder actually filled afterwards. And significant filling was observed, with unadapted planned CTVs failing to cover the bladder 49% of the time, whilst 97% of adapted plans successfully covered the extended volume. Similarly, for Rodi et al. At Peter MacCallum also performed an ART trial on the bladder and found that the volume of healthy tissue receiving more than 45 gray decreased by 29% compared to the standard treatment. Chai et al. Also looked at the bladder, and they found that the unadapted plan was seen to have a lower target coverage than the adapted plan, whilst using almost double the PTV. So you can see the statistics here. There is more coverage with the adapted plan and way less of a planned target volume, so you're irradiating way less healthy tissue. And similarly, Hawkins et al. Performed an ART for 14 esophageal cancer patients, and again we see the unadapted plan having a lower target coverage success rate, whilst using a much larger PTV, as can be seen in this table. And more importantly, the half dose reduction, there's a 22% dose reduction there, and also the B20 lung dose reduction, a 34% reduction to those organs at risk. So before I conclude, I just want to highlight again that the aim of this project is to improve CBCT image quality so as to, I guess the first direct and more accessible application is to compare the delivered dose on the day as to the initially planned dose. And if it's seen that over time, over many different treatments, the delivered dose deviates significantly from the actually planned dose, then I think there's an issue in the actual treatment protocol, and I think we need to look deeper and think about how we can correct that. And judging from the literature based on adaptive radiotherapy, I think it's a very good way to go about it, and to actually improve the outcomes for patients, and also improve the outcomes for the hospital and just everybody, I guess. And yes, this is a bit of a mess, but this is I've tried to combine everything in one image. This is where I'll leave it. Thank you, everyone. Do you have any questions?
This is great. So you talked about motion artifact. So why might, if we're doing a CBCT on a linac, why would motion be a particular problem?
So motion it can be voluntary or involuntary, and I guess you can always use certain, I know they have certain straps, I don't want to say straps, but you can hold the patient. They can be immobilized. But involuntary motion such as the heart and breathing, respiratory motion, that can't exactly be stopped, and so there are techniques to overcome that. But the thorax actually presents one of the largest issues with CBCT acquisitions because they take so long. They take something like a minute, and there's no way you can actually properly. It's not like a normal CT where a normal CT, for example, actually can match, I think, the phase of the breathing and then correct that. CBCTs don't have that, so that would be an interesting way to actually to improve the image quality in the reconstruction phase. You can take image sets from when the lungs are at the same phase, and then that would eliminate motion artifacts. But yes, motion artifacts cause double contours, or if I don't think it was evident in the image, but for example, bowel movements, gas trapped in the bowels, that again is involuntary, and it creates streaking artifacts because the reconstruction algorithm assumes that the patient is static, obviously, and that every photon ray passing through the patient corresponds to a static anatomy. But when it changes, that obviously messes things up in the reconstruction phase, and it results in pretty nasty streaking artifacts.
So do you know why the CBCT takes a minute?
I think it's to do with the international protocols. I'm not exactly sure why they have made it that way, but it's not in our power to change that, unfortunately. But I'll have to look into that more, and I don't think we can change the international protocols.
You're in the right area, so it's to do with the speed of the rotation of the gantry. It's limited to a maximum of 1 revolution per minute for safety reasons.
And I'm also guessing instabilities might result if it was any faster.
Well, it's mainly safety, so people don't get which body sites might you focus on if you're doing like if you had to choose two, for example, which two might you choose?
Typically there's the head and neck region, there's the thorax region, midsection, and also the pelvic region. I think the head and neck region actually, since it's compared to the other sites, it's not as thick, and the images aren't that bad, and even soft tissue contrast, it's nowhere near as good as CT images, but it's very workable. But the thorax and pelvic regions are very problematic for CBCTs, and I think whatever results I come up with would be best served on looking at the pelvic and thorax regions, because the scatter conditions there are so much greater, just because of the cone beam shape, and by nature of the larger volume irradiated, more scatter occurs and more artifacts result. So I'll have to liaise with Charlie's and get a substantial number of data sets. I'm thinking, obviously the more the better, I think, because that covers a wider margin of different types of patients and different types of tumours. But I'm thinking, rough number, maybe 15 for. I would have to be looking also at the same tumour site to make the analysis consistent. I would like to focus on the prostate for the pelvic region, and for the thorax region, I think it's more difficult there because other modalities may be more effective at treating lung cancers, that kind of thing. But I will have to look deeper for the thorax region. But I'm thinking, obviously as many patients, the more patients the better. But I think that.
One more thing. So you're eventually thinking about the accuracy of those calculations. But then considering that the image quality is different on a CT compared to a CBCT, and the accuracy is not lining to the doctor. So then your structures will be
Are
you using the same structure set of the CBCT?
So assuming the CBCT quality is up there, it's very high, you're asking if the anatomical differences will actually result in the differences in dose between the planning CT and the CBCT.
Planning system, then you give the planning system different structure, it calculates the different amounts.
Yes, I think this is where deformable image registration comes in. In an ideal scenario, there would be a planning CT taken on the same day as a CBCT to minimize anatomical differences. However, I foresee that might be a problem at this institution, so I think it's better to actually either deform the planning CT to match the CBCT. That may incur some errors, but that would, in theory, minimize the differences in anatomy, and then you would be purely comparing the image quality between the planning CT and the CBCT. Or you could do it the other way, you could deform the CBCT to the planning CT, but again that would induce some error. So I think I will have to, I know other authors have addressed that with taking a planning CT within the same day. I mean, I could just take one of the first images, if a planning CT occurs on day 1 and a treatment occurs, I don't think it would occur on day 2, but as close as possible to the planning CT to minimize anatomical differences.
Thank you very much for the presentation. Maybe would like to add to that question, that's the question that I wanted, but I'm maybe making it broad. You indicated that maybe the CT numbers might be an issue in terms of dose calculation, maybe something that is hampering the development of ART. Is there anything else that you think maybe needs to be resolved from a practical perspective that makes it maybe more acceptable and easier to implement?
Adaptive radiotherapy?
Yes.
Anything else other than the HU?
Yes.
So, yes, I think the time constraints for medical physicists and radiation oncologists to delineate the organs for every single CBCT, so then you can see, as with the previous treatments, they had a library of plans, small, medium, and large contours, and they overlaid that onto a newly delineated CBCT, and then they see, okay, this is, this plan fits better, therefore I'll use it. And they did come up with better results. However, I think the time taken to delineate all of those new CBCTs is it puts everyone under stress. So I think the most promising method is actually the deformable image registration. So you deform the planning CT with the contours to the CBCT, and that automatically deforms all of the contours, so that saves a lot of time. And that's one massive hurdle. In terms of other hurdles, I think other authors have looked at other ways to actually adjust the treatment parameters, so actually to modify the actual, the volumes of the treatment itself, and that requires a lot of computational nuance, and it's beyond the scope of this project for now, but I would love to dig my teeth into that, hopefully after I correct these images.
Thank you very much.
No problem. Anyone else?
When you were talking about the different types of reconstruction, you were saying that the iterative reconstruction produces a better CBCT image. Does it, is there a high radiation dose given in the acquisition when you're applying an iterative reconstruction, or is it a different, application to the same data?
So the physics behind the acquisition itself is exactly the same. It's what happens after that is different. And in fact, there was a study that came out that they used a quarter of the data points as compared to a standard CBCT acquisition, except they used iterative reconstruction. And because of the nature of iterative reconstruction, it modifies it a little bit, and then it iterates and compares to the error matrix and modifies it a little bit again. Even with a quarter of the data points, it still produced an image. I won't say it's as good as the filtered back projection, which used all of the data points, but it was in terms of IGRT applications, as in just patient positioning, it was up there. You could easily be used for that. And so that effectively means a reduction of a quarter, by 75% reduction of the dose. Yep. So iterative actually increases image quality and has the potential to decrease the dose. Yes, go.
Yeah, maybe my next question, hopefully the last, is we're talking about the limitations, that something that's limiting the maybe quick development of ART. Here you're using combined CT, and I understand there is also MRI-based image-guided and also adaptive radiotherapy. And because many centers have got combined CT, do you think that
it will be superseded?
It will be superseded by MRI-based treatment?
If there was infinite money in the world, maybe. I think, practically speaking, I struggle to see that happening because an MRI is a very expensive and highly technical machine. To couple that with a linear accelerator, I'm not actually sure if the MRI as well as the LINAC, it's on one system. If that's the case, that's an even more expensive system. Look, I think that could be the future if they decided, manufacturers and the community decided to full-heartedly commit to adaptive radiotherapy. That is the future. But currently, at least for the foreseeable future, I think with institutions, pretty much all LINACs having CBCTs, I think it's worthwhile to try and get the most out of them. I know CBCTs weren't initially designed to be used for adaptive radiotherapy, but they do show a lot of promise, at least in certain anatomical regions. I think a result from my paper, from my research, would be that it's probably not applicable for all regions, or different methods, different correction methods are better for certain regions than others, and that's valuable information that I have not been able to find in the literature thus far.
Yeah, that's a good point. Maybe what I would recommend is that it doesn't focus of your study to look at maybe adaptive radiotherapy using MRI-based LINACs or adaptive radiotherapy. It's good to just allude to know that those things are there, and also to justify that the world is using combined CT, and that's what is there at the moment. It's better to utilize what is there. I think it's a good thing to
emphasize that point, or to compare the two?
Not maybe to compare such, but to be aware, to make sure that people or whoever is reading know that you are aware of those things. There is no way they evaluate.
Okay. Yeah, absolutely. Yes, absolutely.
But next time is the MR LINAC.
Awesome. Okay, thank you. Thanks everyone.